Assalamualaikum and a very good day to all. So now we are going to discuss the topic 6, which is current and resistance. Okay, in this chapter, we are going to look deeper with the relationship of the current with the number of electron, with the current density, with the drift velocity. And after that, we are going to understand how the resistance affected by length and also area. Okay, and then we are going to discuss about the current affected by resistance and voltage, and also the last one going to be the electric power. Okay, so let's start. Okay, so we are going to start with current and current density. Okay, so we know that the current represented by I, so the relationship current with the number of charge is current is going to be how many charge passing through that given time interval. Okay, so example, if you have like 2 seconds, you measure in 2 seconds. So example, in 2 seconds you have 50 coulomb, so means that there is the amount of charge that passing through in that time interval. Okay, so the current are going to be represented by I, and also the unit going to be ampere. Okay, so the things that you need to understand with the current is current relate with charge. It means that charge cannot be created, cannot be destroyed. So it's basically about the conservation of charge. Okay, so there are misconception where, example, if you measure at the first round, you measure is going to be 2 ampere, and suddenly when you put some resistance over there, and based on our knowledge, resistance is the one that going to give some obstacle to the current to flow. So after that, maybe you measure is going to be 1 ampere. So most of the people thinks that the current are going to be used up by the resistor, which is totally wrong. Okay, the things that you need to understand here is it's not being used up, because now you are measure with the same time interval. Example, if you measure at 1 second, and then you are going to see that you get 2 ampere, and then when you put the resistance at 1 second, you measure, you are going to get 1 ampere. It doesn't mean that the current is used up. It means that the number of charge that passing through going to be less, is because of there's a lot of obstacle when this current pass through. Okay, but still, if you have 50 coulomb going into one junction, definitely is going to come up with also 50 coulomb, because based on conservation of charge. Okay, okay, example like this one. Okay, you can see that this question is quite easy. Okay, this question asks you about how much total charge pass by the given point in the circuit during those 4 minutes. Okay, the things that you need to understand here is always make sure that you change any physical quantity into SI unit. Okay, so 4 minutes, you make sure that you change that into second first. Okay, so you're going to be 4 minutes, so you have 1 minute equivalent to 60 seconds, which is going to be 240 seconds. Okay, so because the question asks you to find the total charge, so you can actually use the formula of I equals to Q over T. So Q is going to be right now the question, okay, the question asks you to find Q, so Q equals to IT, so I is going to be 2.5 times 240, so you are going to get the answer is 600 coulomb. Okay, next the question asks you to find how many electrons will this be. So now you have like 600 coulomb. So as we know that, okay, one electron going to be equivalent to 1.602 power of negative 90 coulomb. So now the question asks you to find how many electrons. So 600 coulomb, so how many electrons? So means that 600 divided by 1.602 power of negative 19, therefore you are going to get your answer is 3.80 power of 21 electron. Okay, so the things that you need to understand here is current is scalar, not a vector, but then the current actually flow from positive to negative inside the circuit. So example, if you have like one closed circuit, okay, one closed loop, so the directions of current will be from positive to negative. Okay, but the directions of the electron will be opposite, which is from negative to positive. So this is directions of electron. Okay, but there are some people going to ask why the directions of electron different with the conventional current flow. Okay, the reason is because of the first one that find this concept thought that current flow from positive to negative. At that time, these people didn't find the concept of electron yet. Okay, so few years after that, then they discovered that, oh, electron is basically moving from negative to positive. But we actually follow from the first one that find this concept, and till now we still follow that concept, and that's the reason why the directions of the current will be opposite with the directions of electron, even though based on our understanding that when the electron move, then definitely there will be a current flow. Okay. Okay, so like I mentioned before, the directions of current flow from positive to negative we call as a conventional current. Okay, but when we want to talk about the directions of electron, definitely we are going to state electron flow. Okay, so now we are going to talk about the microscopic view of drift velocity before we proceed with the effect of resistance and voltage to the current. Okay, so let's start. Okay, so when you connect wire made of conductor to the battery, so definitely this battery are going to give some potential difference to the wire. Okay, so this wire are made of conductor, which mean that before this, when we talk about static electricity, the inside the conductor, E always be 0 for static. However, now we are going to talk about the movement of electron. Therefore, inside the wire, E are not going to be 0. Okay. So, before you connect the wire to the potential difference, what happened to the electron? Electron are going to like moving randomly. Okay, and once you connect to the battery or any power supply, you are going to set some electric field inside the wire. Okay, so the directions of electric field going to be in the same directions of the current. Okay, so because once you set electric field inside the wire, you are going to give some force to the electron. So electrons are going to accelerate, okay, based on Newton's second law. Okay, but the acceleration of electron are not going to be too long. The reason is because the electron are going to collide with the atom of the wire. So what happens to the electron at the time? The energy at the time going to be reduced. Therefore, electrons are going to reach, okay, average steady speed. Okay, which we call this one as a drift velocity. Okay, so the things that you need to understand here is when electrons are randomly moved here, the speed of electron at the time is going to be less than the drift velocity. Okay, now we are going to derive some formula which we are going to relate with current density, with drift velocity, length, and time. Okay, so you have like one cross-sectional area of the wire. Okay, so this is area. Okay, so you have electrons that are going to pass through cross-sectional area of the wire. Okay, which means that at time t, the electrons are going to move with some length. Okay, with some length. So based on our knowledge, velocity going to be length over time. So length going to be length equals to velocity times time. Okay, so as you can see that electrons are passing through a cross-sectional area, which means that area times with length, you are going to get some volume, which means that electrons are going to pass through some volume of the wire. Okay, so you can see that volume will be equals to area times length. So length here you are going to insert into this formula. Therefore, you are going to get volume equals to area times velocity times time. Okay, so now we are going to relate this formula with the number of electron, because you can see that there will be a lot of electron inside the wire that going to pass through this volume of wire. Okay, so we have this one formula which is number, oh no, sorry, we call it as the charge density, which is number of charge or number of electron per unit volume. Okay, so this is basically charge density, or we can call it as the number of charge per unit volume. Okay. Okay, therefore the volume here we are going to insert into this formula, because after this, okay, we already find the charge density. Now we are going to find the total charge. Okay, so the total charge going to be Q equals to number of charge multiplied with the charge per particle. It can be electron, it can be proton. So now we are going to talk about electron, therefore I'm going to put electron with a negative there. Okay, so here and here we are going to get from this formula, which means that we are going to get N equals to N times with the AVT comes from this one. Okay, so you are going to insert all this thing into this formula, which means that you are going to get NAVT with the electron here. Okay, so now we are going to find the relationship of total charge with the current, which I mentioned before. The formula going to be current equals to charge per unit time. Okay, so we are going to insert into this formula. So we are going to get an AVT with the negative E here over T here. So we are going to cancel that. So therefore the current here we are going to get NAV negative E. Okay, so like this one, okay, and we have the charge density. The current also have current density. Okay, the current density are going to be represented by J. Okay, so J is going to be current per unit area. Okay, so that's why we call this one as a current density. Okay, so we are going to insert this I into this one. Therefore, we are going to get here is an AV negative E over area. So we are going to cancel that. Therefore, the current density going to be NVE. Okay, to differentiate with the velocity, the normal velocity, therefore we are going to put D here to represent the velocity. Okay, so that is basically the formula that you are going to use to answer the question that going to relate with the number of charge or number of electron. Okay, so now we are going to answer the conceptual questions. So the question asks you to find what is the directions of the current. Okay, so now we have this movement of electron, which based on our understanding, the movement of electron always be from negative to positive. Okay, like this. Okay, so are the following leftward or rightward for the current? So the directions of current definitely are going to be opposite to the directions of electron, therefore it's going to be rightward. Okay, so how about the current density? Okay, the current density is going to follow the directions of the current, which means that also rightward. Okay, and how about electric field? Same thing, also rightward, which is moving from positive to negative. Okay, now we are going to discuss the conceptual question 2, which this one, the question asks you to find what happens to the current density, the electron drift velocity, and charge carrier density when you double the current. Okay, the things that you need to understand, when you double the current, this one doesn't affect the number of charge carrier density, because the charge carrier density, it depends on the material. If you change the material, definitely the number of charge carrier density will be different. Okay, therefore, because this one we assume that is going to be constant material of the wire, therefore the charge carrier density here will be constant. Okay, but when you increase the current, what happens to the drift velocity? It will be increased, because when you increase the current, it means that this one affected by the voltage. Okay, so the potential difference will be increased, therefore the current will be increased, therefore the electrons are going to aggressively move. Okay, and that's the reason why the drift velocity will be increased. Okay, so what happens to the current density? Okay, so based on our understanding, J going to be I equals to A. Okay, so when the drift velocity of the electron increase, so what happens to the amount of charge passing through the cross-sectional area? It will be increased, because at that time, when you measure at that time with the electron that moving with the high speed, therefore charge passing through the cross-sectional of wire will be increased. So the increase of current definitely increase of current density. Okay. Okay, now we are going with the calculations of the current density question. Okay, so now we are going to find first the current density inside the wire. Okay, so you have the copper wire, which is 3.2 millimeter in the diameter, carries a 5 ampere current. Okay, and they already give you the atomic mass, the density of the copper, and the resistivity of the copper. Okay, so for you to find the current density in the wire, you can actually use the formula of J equals to I over E. Okay, J equals to I over A. Okay, so for the area here, because we assume it's going to be circle, therefore it's going to be pi r square. So make sure that you change millimeter into meter first. Okay, so you have 5.0 over, this one is diameter. Okay, so it's going to be pi 3.2 power of -3 divide by 2, because you need to find the radius square. Okay, so from here you are going to get your answer is 6.20 power of 5 ampere per meter square. Okay, for you to find the derived velocity, okay, so we already have the current density. Okay, so we can actually find the derived velocity based on formula of J equals to NEV. NVE. VE, or maybe I change the E to Q. Okay, number of charge. Tapi here they are talk about electron, and therefore I can actually put E over there. Okay, so for me to find the derived velocity here, I need to know the charge density first. Okay, so we know that charge density or charge per unit volume going to be capital N over volume. Okay, so volume here you can actually use the concept of density mass over volume, because this question already give you the mass, the atomic mass of copper, and also the density, therefore you can actually find the volume. Okay, so here I'm going to find the volume, which is going to be N equals to N over mass over density. Okay, so copper have 1 free electron per unit atom. Okay, so 1 free electron will be, here is going to be 1 mole, and this is going to be 1 mole, which is 1 mole equivalent to 6.02 power of 23 free electron. Okay, so I'm going to put 6.02 power of 23 here. Okay, therefore the mass here going to be the atomic mass, which is I'm going to convert that into kilogram, 63.5 divided by 1000 to convert that into kilogram, and also divide by density of the copper, which is 8.90 power of 3 kilogram per meter cube. Okay, so from here you need to find the charge density first, which is going to be 8.44 power of 28 charge per unit volume. Okay, charge density, which is going to be here, I put it as a meter cube over meter cube, sorry. Okay, okay, so now we are going to find the derived velocity. Basically we are going to use this formula. Okay, so J, okay, so derived velocity will be J over NQ. Okay, so J here I already find it at the question A, which is going to be 6.20 power of 5 divided by the 8.44 power of 28 times with the charge of the electron, which is 1.602 power of -19. Okay, so you are going to get your answer is, okay, so it's going to be 4.59 power of -5 meter per second. Okay, for question C, we are going to answer that after this, after you have learned about the relationship of the resistivity with the electric field. Okay, okay, so now we are going to talk about the resistance and the effect of resistance to the current and also voltage. Okay, so the things that you need to understand here is the resistance, current, and voltage are going to be combined with this one concept we call as the Ohm's law. Okay, so what happens to the current when you increase the voltage? Okay, the current also increase. Okay, so the reason is because when you increase the voltage, example, you are going to increase the difference of height between these two terminals, which is positive and negative. Okay, so this one, when the electron actually move, is going to freely move in compare if we have the same level of potential difference. Okay, and that's the reason why when you increase the voltage, you are going to increase the current. Okay. Okay, you can assume that the flow of current seems like a flow of water. So example, if the river is nearly level, so you can actually see that the flow rate going to be smaller. Okay, but example, if you have different level of river, therefore the flow rate of water going to be increased. So you can actually say that it's same as the battery. When you have a high potential difference come from the battery, definitely you are going to have a high current flow inside the wire. Okay, so the current doesn't affect by voltage only, it's also affected by the resistance. Okay, based on the Ohm's law, V equals to IR, which means the current also affected by the resistance. Okay, so increase value of resistance, it means that they are going to give you a high obstacle to the flow of current, therefore the flow of current going to be reduced. Okay, so however, the voltage and the current doesn't affect the resistance. Is resistance only affected by their material and also length and also cross-sectional area of the wire, but that one I'm going to explain that after this. Okay, but the things that you need to understand here is the current when it comes to the Ohm's law is going to be like current directly proportional to the voltage, inversely proportional to the resistance. Okay, and the resistance are going to be represented by this kind of symbol, which you are going to see this symbol a lot in the circuit. Okay, so this one is the way for you to find the value of resistance. Okay, so we are going to have like 4 or 5 colors. So the first one and the second one going to be the digit number, so you can actually see from this table. Okay, and the third line going to be the multiplier. Okay, so it's going to be times 2 times 3 times 4 like that, and the last one going to be the tolerance. Okay, so now if we want to read this resistor, so it means that the red going to be 2, the green going to be 5, and the multiplier there are going to be yellow, which is power of 4. So the tolerance going to be plus minus silver, which is 10%. So it means that the resistor can stand below or more than 10% value. If not, if more than 10%, what happens to the resistor is going to be burned. Okay, so it means that for you to choose the resistor, it depends on the value of current inside the wire. If the current is too large, therefore the resistor cannot stand that, therefore it's going to be burned. Okay, so this one, okay, the question asks you to find the potential whether it's high at point A or point B. So now they already give you the flow of current, which means that we already know the flow of current always be from positive to negative, therefore higher going to be at point A. And then what about the current greater at point A or point B? Okay, like I mentioned before, current is basically follow the direction, follow the concept of conservation of charge, which means that the flow of current always be constant from A to B. Therefore, A to B, which means that the current will be same value. Okay, so this one, A equals to B, same value at A and B. Okay, so we have this one question, which is basically easy also. Okay, so this one, the question asks you to find the resistance of the bulb. Okay, they already give you the current and also give you the voltage. Therefore, based on the formula of Ohm's law, V equals to IR, which means that resistance going to be V 1.5 over 300 milli. Therefore, you are going to get your answer is 5 ohms. Okay, now if you change the battery and the battery become weak and the voltage drop to 1.2 volt, how would the current change? Okay, like I mentioned before, the resistor doesn't depends on the current and voltage, it depends on the material and length and also cross-sectional area. Therefore, you are going to use the same value of resistor, but now you are going to find the current, which is going to be I equals to V over R. So the V going to be 1.2 divided by 5, which means that the current flow only 240 milliampere. Okay, now we are going to talk about the effect of others to the resistance. Okay, like I mentioned before, resistor doesn't affect by current and also voltage. Okay, resistor basically affected by the resistivity, which depends on the material, the length, and also area. Okay, so when you have like longer length of resistance, it means that you are going to increase the resistance. Okay, but when you have a increase in area, okay, like this one, okay, so when you increase the area, it means that you are going to give a lot of space to the electron, therefore the resistance is going to be reduced. Okay, like compare this one, the area is like very small, therefore the atom of wire are going to collide with the electron more, therefore the resistance going to be resistance going to be increased. Okay, so basically this is the value of resistivity. Depends on the material itself. Okay, and then we are going to discuss after this the effect of resistivity to the temperature. Okay, so before we proceed with the next part, we are going to answer this one first. This one, the question asks you to find what diameter copper wire should you use to keep the resistance less than 0.10 ohms per wire. Okay, so means that based on our understanding, resistance will be resistivity length over area. So the question asks you to find the diameter. Okay, so now resistance here is going to be 0.10. The resistivity going to be 1.68 power of negative 8, and the length going to be 20 meter. So we didn't know the area. Okay, so we find the area first, which we are going to get here is 3.36 power of negative 6 meter. Okay, so for you to find the diameter, so therefore you're going to get area equals to pi r square, which is going to be pi d square over 4. So we need to find the diameter here, which is going to be 4 times 3.36 power of negative 6 over pi. Then square root everything. Supposedly you are going to get your answer is 2.07 power of negative 3 meter for the diameter. Okay, good. Okay, question B. What is the potential difference or the voltage drop across each wire? Okay, so we already have resistance. So we already have the current, therefore we can actually find the voltage. So voltage going to be IR. So the current is 4 times with the resistance 0.10. Therefore you are going to get your answer is 0.40 ohm. Volt. Okay. Okay, now we are going to discuss the effect of resistivity to the temperature. But as you can see that from here, there are some value of temperature is going to be negative here. The reason is because there are some material where the temperature over there is used to break the bonds between the ion or atom, and that's the reason why the temperature are going to be lower. Okay, which means that the increase of temperature doesn't increase the resistivity, but like other things, when you increase the temperature, definitely your resistivity will be increased. Okay, so now we are going to derive some formula for this one. Okay, so basically the things that you need to understand here is the change of resistivity. Okay, the change of, okay, I put here as the change of resistance first, okay, because we are going to relate that with the resistivity. Okay, the change of resistance going to be affected by the original value of resistor. Okay, if you have like large amount of resistor value, definitely the change going to be increased, something like that. Okay, and then it's also affected by the temperature coefficient, which is this one, okay, the alpha here, and also affected by the change of temperature. Okay, so large change of temperature definitely going to affect more to the resistance. Okay, so it means that for you to find the new resistor, which is I'm going to put here as the R, is going to be the change of resistor plus with the original resistor. Okay, so you are going to put this one into this part, therefore you are going to get here is R naught alpha temperature plus R naught. Okay, so we are going to factorize that, therefore you are going to get the equation is R naught 1 plus alpha change of temperature. Okay, just rearrange everything. Okay, so here, as we know that the resistor formula affect which is relate with the resistivity going to be our resistivity length over area. So I'm going to put that into both this one and this one. Okay, so I'm going to get here is resistivity length over area. Okay, so this is the new value of resistivity and this is the new value of resistance. Okay, is going to be this one is resistivity not this one is going to be the original resistivity length over area 1 plus alpha temperature coefficient change of temperature. Okay, so because length and also area we didn't change that, so we can cancel that one. Therefore you are going to get the formula of resistivity, which should be the change of resistivity will be equivalent to the original resistivity 1 plus alpha change of temperature. Okay, and please take note temperature here need to be in Celsius. Okay, and the things that you need to understand here is the initial value of temperature here, because T minus T naught, right? Okay, it can be 0 degrees Celsius or it can be 20 degrees Celsius. Okay, that's the things that you need to understand. Okay, the reference temperature. Okay, now we are going to answer the questions that relate with the temperature. So now the question asks to find what is the temperature of this solution when your resistance change from 164.2 to 187.4. Okay, so we are going to use the formula of resistor, which is resistor equivalent to resistor 1 plus alpha change of temperature. Okay, so the here 20 degree Celsius is your reference temperature, which is that one going to be your initial temperature. Okay, so here going to be 187.4 equals to 164.2, 1 plus, okay, alpha here 3.927 power of negative 3. Change of temperature is from T minus 20 degree. Okay, okay, like that. Okay, so now, okay, you already have that, so basically you can actually get the form answer, which is T going to be 55.97 degrees Celsius. Okay, as easy as that. So it depends. If the question give you resistivity, therefore you are going to use the formula of resistivity original 1 plus alpha change of T, or if the question give you resistance, then directly use this formula. Okay. Okay, so like I mentioned before, we already talked about the Ohm's law, but this one we are going to talk about the characteristic of the Ohm's law. Okay, so the Ohm's law, it means that the current are going to be directly proportional to the voltage. Therefore the graph here are going to be like this. Okay, the increase of voltage definitely increase of current. Okay, increase of. But when it comes to the non-Ohm's law, okay, or the other name is non-ohmic law, the increase of voltage not going to be directly proportional. It's going to be like slightly curved like this. So means, example, if you have a 20 volt voltage, doesn't mean that the current going to be increased with 20 ampere. It's going to be like maybe 21, 25, something like that. Okay, okay. So there are certain material that can be categorized as non-ohmics, which is tungsten. Okay, tungsten is basically inside the filament of the lamp. Okay, that one is basically made of non-ohmic. Okay, because when you apply some current, when you apply low current, it's going to be increased a little bit, but when you apply large current, it's going to heat up a lot. Then that's the reason why how the light is basically produced. Okay. Okay, so basically this is the graph and the difference between ohmic and non-ohmic. Okay, and like I mentioned before, non-ohmic, one of it is going to be tungsten. Okay, so the resistor, the ohmic, where the current are going to be directly proportional to the voltage. However, for the non-ohmic, the current are going to be increased non-linear with the increase of voltage. Okay. Okay, now we are going to derive the formula that are going to relate the electric field with the resistivity and also current density. Okay, so we have the Ohm's law formula, which is V equals to IR. Okay, and from the chapter 4, V going to be equals to ED. Okay, which means that I'm going to change D into L. Okay, because length of the wire. Okay, so I going to be relate with the current density, which is J equals to I over area. Therefore, I'm going to get here is GA. And the resistance over there going to be relate with the resistivity, length over area. Okay, so length here can be cancelled out. The area also can be cancelled out. Therefore, the electric field here, you are going to get the formula is J times resistivity, which means that the current density going to be electric field over resistivity. Okay, so the opposite of the resistivity is going to be conductivity, which is very good conductor. So resistivity will be equals to 1 over conductivity, which when I put it inside this formula, I'm going to get the current density will be E times with the sigma conductivity, and the unit for the conductivity will be over ohm meter. Okay, so now we are going to answer the conceptual questions that are going to relate with the resistivity. Okay, so the question asks you to find the effect of electron drift velocity when there are certain physical quantity that are going to be increased and also constant. Okay, so for this question, I'm going to derive the formula, because from the formula itself, I'm going to get the answer. Okay, so I'm going to start with the formula, which is for us to find the relationship of the current of the area and also line, which is come from the resistivity. Therefore, I'm going to use the I equals to NA drift velocity with the charge, okay, or the electron, it depends. Okay, so drift velocity here, because we need to find the effect of others to the drift velocity, so I over NA Q. Okay, so I here, I'm going to relate with the Ohm's law, which is V equals to IR. I going to be V over R K, because now you can see that there's a and L constant, so therefore we need to use the resistance here, which is resistivity length over area. So V equals to resistivity length over area. Okay, I'm going to put this formula into this one. Okay, therefore I'm going to get my answer is going to be VD equals to voltage over density length over area times 1 over Q. Okay, so the area here can be cancelled out. Okay, and then I'm going to get my answer is V, which is voltage over the resistivity length, charge density, and also Q. Okay, so now the first question. Okay, when you increase V, but A and L going to be constant. Okay, so we are going to use this formula. A, okay, doesn't have in our formula, so it doesn't affect. So L going to be constant, but you increase the voltage here. What happens to the drift velocity? The drift velocity will be increased. Question B, you increase the length, but the voltage and the area will be constant. Okay, so we have the formula VD equals to V over resistivity length and Q. Okay, the area constant, okay, area doesn't affect, but the voltage is constant, but you increase length. Okay, when you increase length, what happened to the drift velocity? Yes, drift velocity will be decrease. Okay, and then decreasing A. Okay, based on our formula here, there's no A over there, so when A of increase or decrease, it doesn't affect our drift velocity. Therefore, our drift velocity will be constant. Okay, next. Okay, so this one, okay, this is the question that we already answered previously, but the question C, we need to answer it now because you already learned about the resistivity and the effect to the electric field. Okay, so the question asks to find what is the electric field inside the wire. Okay, so the formula for electric field with the resistivity going to be J equals to electric field over resistivity. Okay, so the current density we already get from the question A, which is going to be 6.20 power of 5, and the resistivity is 1.68 power of negative 8. Okay, so you are going to get your electric field is 1.0 power of negative 2 volt per meter. Okay, Okay, so now we are going to answer this question. Okay, the question asks to find the current density. Okay, so we already have the current here, so we can actually find J equals to I over A. But the things that you need to be extra alert and be extra careful is now the question states square, which means that it's not going to be pi r square, it's going to be only L square. Okay, so I over L square. So the I there are going to be 3.6 and the size is 2.3 millimeter. Change that into meter first. Okay, always change into SI unit. Okay, so 2.3 over 1000 square. So you are going to get your answer is 6.81 power of 5 and the unit is ampere per meter square. Okay, next, the magnitude of the electric field in the wire, and the question already gives you the resistivity. So we know that the relationship between current density, electric field and resistivity will be J equals to electric field over resistivity. So E going to be J, which is current density, power of 5, times with the resistivity, which is 1.72 power of negative negative 8. Okay, so you are going to get your answer is 0.0117 volt per meter. Okay, next. Okay, so the question asks you to find how much time is required for an electron to travel the length of the wire. Okay, so the question asks you to find time, which means that you can use the formula of okay, you find first the derivative velocity, which I'm going to I equals to NAVDQ. Okay, so we find the derivative velocity because from there we are going to find the time. So I is 3.6, charge density, which is density of free electron, is 8.5 power of 28, and the area here you are going to find 2.3 over 1000 square, and then the velocity and the charge is going to be 1.602 power of negative 19. So you are going to get this one is 5 power of negative 5 meter per second for the derivative velocity. Okay, so from there you can actually find the time, which is, we know that the velocity is length over time. Okay, so time going to be length is 4 meter and the velocity is 5 power of negative 5. Therefore you are going to get your answer is 8 power of 4 second. Okay, so that's how you do it. Okay. Okay, so we are going to talk about the last part, which is going to be electric power. Okay, so you need to understand that power is basically how many energy has been transformed to the other form of energy. Okay, because we talk about the resistor. Okay, so we know that the resistor are going to convert the electrical energy into heat or thermal energy. Okay, so now we are going to derive the formula. Okay, we know that power is going to be work done per unit time. Okay, or if you want to find the instantaneous power, is going to be delta W over delta T. Okay, so we know that from the chapter 4 is going to be voltage going to be work done per unit charge. So I'm going to put that into this formula. I'm going to get my formula is delta Q over delta T voltage. Okay, because okay, we know that this one is basically formula for current, because current is charge per unit time. Therefore I'm going to get my formula is P equals to IV. Okay, you can use other formula for power where we are going to use the concept of Ohm's law. Okay, I'm going to put the V here. Therefore I can also use power equals to I square R, or I can actually put I as a subject, V over R. I can use power V square over R. Okay, and that's also the formula that you can actually use. Okay, the things that you need to understand here is when you pay the bill, the electrical bill, is basically, it's not you pay the bill for the power, is basically you pay the bill for how many energy has been used, which means that if we have a lot of electrical equipment, it means that there are going to be a lot of energy has been transformed, which means that your bill going to be higher. Okay, so it means that you are going to pay more. Okay, okay, so now we are going to calculate for using concept of power. Okay, so the first one going to be the question asks you to find the resistance, and the question already give you the 40 watt and also 12 volt. Okay, the unit for power is basically watt, so you can actually use the formula of P equals to V square over R. Okay, so the V square is going to be 12 square, which is 40. Therefore, you are going to get your answer is 3.60 ohms. Okay. Okay, now we are going to calculate the charge. Okay, when we use the electric heater, so the electric heater are going to draw a steady current of 15 ampere, and the voltage that we are going to use is 220 volt. Okay, so the question asks you to find how much power does it require and how much does it cost. Okay, so for you to find the power, you can actually use power equals to IV, which is 15 multiplied by 120. So you are going to get your answer is 1800 watt, or 1.8 kilowatt. Okay, so now we are going to find how much that is cost per month. Okay, so you have 1 month is 30 days and it operates 3 hours per day, and the electric company charge 9.20 cents per kilowatt hour. Okay, so we need to convert that 9.20 cents into dollar. Means that you are going to have 0.092 dollar per kilowatt hour. Okay, so now we are going to find how much that it costs. It means that 0.092 dollar per kilowatt hour. So it's going to operate 3 hours per day, and then it's going to, we need to find per month, which is times with 30. Then don't forget to multiply by 1.8 kilowatt, because 1 kilowatt are going to cost you 0.092 dollar. Okay, so you are going to get your answer here is $15. Okay, that's how you do it. Okay. Okay, we are going to proceed with the last question here. Okay, so the question asks you to find the power delivered to the toaster, and the question asks you to find the final temperature of the heating element. Okay, so the question already gave you the voltage and the current, and the question asks you to find at operating temperature. Okay, so it means that we are going to use P equals to IV, which is I is going to be 1.53 and the voltage going to be 120. So you are going to get here is 1.53 times, we're going to get 183.6 watt. 6 watt. Okay, now we are going to find the next one, which is what is the final temperature of the heating element. Okay, so we have the reference temperature at 20 degree. The current here are going to be 1.8 ampere, and when it reach with some temperature, is going to reach with the value of 1.53 ampere. Okay, so we know that the resistance going to be R equals to R naught 1 plus alpha change of temperature. So they give you voltage and current, so we know that from the Ohm's law, V equals to IR. Means that the R going to be V over I. This is the operating temperature, and this is going to be the reference temperature, V over I naught. Okay, 1 plus alpha change of temperature. So the V here going to be 120 divided by the current of the operating, which is 1.53, equals to 120 over 1.8. 1 plus alpha here going to be 0.4 power of negative 3. Okay, and the temperature is going to be T minus 20 degree. We're going to get here is 461 degrees Celsius. Okay. Okay, I think that's all for now. So if you have any questions, feel free to ask. So I'm going to see you again with the next chapter. Okay, so Assalamualaikum and goodbye.